Hypothesis testing is a decision-making process. Now that we have gone through some basic hypothesis tests, we need to examine the ramifications of the decisions we are making through the process. Hopefully, the decisions we make are correct ones, but sometimes they are not, and it is possible that we make errors. These are formally called the rather unimaginative names of Type 1 and Type 2 errors. This slide program is intended to add the human element to the process we are learning. It is less about math and more about your knowledge of how the world works. The typical hypothesis testing process works like this. You have a conjecture backed up by some data. You create the null hypothesis, which usually says that your conjecture is not true. Your alternative hypothesis is that your conjecture is true. Either the null hypothesis or alternative hypothesis must be true. It usually is impossible to know with 100% certainty which one is true. You analyze your data, and from that analysis you find a statistic. Based on your sample data, it could be a z, t, or chi-square statistic. From there, using tables or your calculator, you find a p-value. You compare this p-value to alpha, which is usually 0.05, but can change depending on the standard used. If the p-value is less than alpha, you reject the null hypothesis and accept the alternative hypothesis. If the p-value is greater than alpha, we fail to reject the null hypothesis, meaning that there is not enough evidence to conclude that the null hypothesis is not true. Although that is not precisely saying that the null hypothesis is true, in absence of any alternative, that ends up being our conclusion. Let's see how this process applies to the real world. This is Andrew, a student in your statistics class. He just took a 50-question multiple-choice comprehensive midterm with choices A through E on each question. His statistics teacher has a conjecture. She has strong suspicions that Andrew cheated in the exam. This is why. Here is why the teacher believes that Andrew cheated. We can think of it as the evidence against Andrew. 1. Andrew had a 92% in his test, 46 questions correct, and 4 answers wrong. 2. Andrew has been doing barely passing work throughout the year. 3. Andrew was seen by a proctor looking at another student's exam. He was warned several times. 4. On the multiple choice test, Andrew got the same problems wrong as the student whose paper he was seen looking at, an A student throughout the year. 5. Andrew's wrong answers were exactly the same as that student's. The teacher certainly doesn't do a formal hypothesis test, but in her mind, she is going through a process not unlike the formal process we detail on the slide. The process is similar to that of a jury trial. We start with the premise that Andrew is innocent, that is, he didn't cheat in this exam. That is the null hypothesis. The alternative hypothesis is that Andrew did cheat on this test. It should be obvious that one of these two statements must be true. It should be pointed out that our system of law is innocent until proven guilty. Although this is not a legal issue, the same process is followed. There are other parts of the world where the null hypothesis might be that Andrew is guilty and he needs to prove his innocence. In our system, Andrew is presumed innocent and we need to find enough evidence to show his guilt. It must also be pointed out that there must be enough evidence to go through this hypothesis testing process. If the teacher is going to formally inform Andrew of her suspicions, she had better have enough evidence to support the alternative hypothesis of guilt. There may be other people who will be hearing the evidence, and you don't want to take up their time unless the evidence is good. You don't want to put Andrew through the stress of the charge against him unless the evidence is good. You conclude that on the surface there is enough evidence to go through this process, and you call Andrew in to go over it with him. You also decide to bring in a school administrator to go through the evidence, so you cannot be called biased against Andrew. There is not a mathematical procedure. There is no calculation of a z statistic or a t statistic. We just need to sift through the evidence. We look at the first two pieces of evidence. Number 2 is not in dispute. Andrew is barely passing the course after a half year, which we presume is based on many quizzes, exams, and assignments. And yet he had a very high grade on this comprehensive midterm. Those two statements are in conflict. Statement 1 is surprising based on the reality of Statement 2. Is that enough evidence to decide that the null hypothesis is incorrect and the alternative hypothesis is? Probably not. Students improve. They decide to buckle down and start working. Maybe his barely passing grade was based on failure to hand in assignments rather than low test scores. From just the evidence of number 1 and number 2, most people would probably agree that there is not enough evidence to overturn the null hypothesis. We now add Statement 3 to the mix. Andrew was seen looking at the exam of the student next to him. Not only that, he was warned. This is visual evidence that Andrew was cheating. Someone saw him looking at another student's paper, not once, but several times. This makes Statement 1 more plausible. He did well because he looked at the work of another student. Still, the teacher didn't see him do it. It was a proctor. It is what is called hearsay evidence. And how do we know that he was actually looking at the paper and not just stretching? Are the three statements taken together enough to overturn the null hypothesis? Now we add number 4. Andrew got the same 4 problems wrong on the test as the student whose paper he was seen looking at. If the other student had a perfect paper and so did Andrew, that would be less surprising than this result. What are the chances that the same exact problems the other student got wrong, Andrew would also get incorrect? Those chances are pretty small. Given the fact that the null hypothesis is true and Andrew didn't cheat, what are the odds that he would get exactly the same 4 problems incorrect as the person whose paper he is suspected of cheating off? He either got those problems incorrect because he cheated, or it was luck. When confronted, Andrew says it is luck. But the chances that it was luck are pretty low. In our minds, we are constructing a p-value, and it is quite small. Is that enough evidence to overturn the null hypothesis? It is possible that it was luck that he got the same problems incorrect. Maybe they were just difficult questions. Is there still doubt in your minds? Finally, the last and most damning evidence. Not only did he get the same 4 problems wrong, he answered them with the same wrong answer as that other student. By sheer guessing, the chances that Andrew would answer any question the same as that student is 1 out of 5, or 20%. So the chances that he would answer 4 questions the same as that one student is 1 out of 5 raised to the 4th power, or 1 in 625. When confronted, Andrew says that it is just plain coincidence. The chance of that coincidence happening is less than 0.2%. Possible? Yes. Probable? No. It really strains the imagination to think that Andrew got the same answers as the student next to him, the student whose paper he was seen looking at, by sheer luck. Still, long shots happen. People win the lottery at more than 1,000,000 to 1 odds. Maybe that happened here. So how do you judge? The last step in a mathematical hypothesis test is to compute a p-value, which is the probability that the results of the evidence happen by chance, and compare it to alpha. If the p-value is less than alpha, we reject HO and accept HA. If the p-value is greater than alpha, we fail to reject HO. Alpha represents the significance level of the hypothesis test. It is the standard of judgment. The smaller the value of alpha, the surer we need to be of our conclusion. In a murder trial, the alpha standard is very small. The 12-person jury must be unanimous. We use the term beyond a reasonable doubt, meaning that any doubt would not affect a reasonable person's belief that the person is guilty. In civil trials, the standard is not nearly as high. Typically, only 9 of the 12 members of the jury need vote guilty. In the famous O.J. Simpson murder trial, O.J. was found not guilty in the murder trial. A guilty verdict would have put him in jail for life, or perhaps even the death penalty. But he was found guilty in the civil trial and was ordered to pay $33 million. The alpha standard was much lower in the civil case, and that's how a conviction was arrived at. In the case of Andrew's cheating, how sure does the teacher want to be? That is a decision that the school administration must make, and unfortunately, it can be impacted by Andrew's family, whether the incident gets any publicity, and how much grief the teacher wants to go through. However, it is vitally important that the alpha standard be chosen. In many hypothesis tests that are handled numerically, alpha is assumed to be 0.05. That is, if the events have less than a 5% chance of occurring by chance, we say it didn't happen by chance, and thus the null hypothesis is invalid. Your conclusion, along with that of the administrator, is that Andrew's explanation of sheer luck to explain the coincidence is so unlikely, you reject the null hypothesis and accept the alternative hypothesis. You conclude that Andrew cheated on the midterm exam. There will certainly be some punishment attached to your conclusion. A 0 in the exam, suspension, or other punishment the school deems worthy will happen. It would be nice if now Andrew admits his wrongdoing, but he insists that he didn't cheat, he was railroaded, and that they are punishing an innocent person. The hypothesis testing is over, but the question is, how sure are you about your decision? Is it possible that you were wrong? And if you are wrong, what are the ramifications of that error? To analyze this, we examine the chart on the slide. First, we have the truth. Either HO is true and Andrew did not cheat, or HA is true and Andrew did cheat. One of these statements must be true. Who knows the truth? Only Andrew, and if you believe, God. This has nothing to do about what Andrew says. The truth exists. Then we have a decision based on the evidence. You either reject HO and accept HA, coming to the conclusion that Andrew cheated, or you fail to reject HO and find insufficient evidence that Andrew cheated. Again, one of these statements must be true. To summarize the last slide, it is best to show the options in a table. Notice there are 4 possibilities. If the null hypothesis is true and you fail to reject it, you have made the correct decision. Likewise, if the alternative hypothesis is true and you reject the null hypothesis, you also have made the correct decision. However, if you reject the null hypothesis and accept the alternative, and the null hypothesis is true, you have made what is known as a type 1 error. And if you accept or fail to reject the null hypothesis, and the alternative hypothesis is really true, you have made a type 2 error. Let's see how these unimaginatively named errors are used in the case of Andrew's situation. If the null hypothesis that Andrew didn't cheat is true, and you find insufficient evidence that he cheated, you are correct. Also, if the alternative hypothesis is true that Andrew cheated, and you find that he cheated, again, you have made the right decision. Remember, though, only Andrew knows whether you have made the correct decision. That is generally true in any hypothesis test. You are making a decision based on evidence. Hopefully, you are right. The type 1 error is concluding that Andrew cheated when he didn't. The type 2 error is concluding that Andrew didn't cheat when he really did. So, what are the ramifications of each error, and in your mind, which one do you think is worse? The type 1 error punishes an innocent person. He may also lose trust in authority, thinking the world is out to get him. The type 2 error allows a person to get away with cheating. He may conclude that he can get away with cheating in other situations, such as insurance fraud or tax evasion. It may lead him to spend time in jail if the behavior continues. Which is worse? That's your decision. As a student, your sympathies might lie with Andrew, as you would hate to be punished for something you did not do. However, as an adult, you may hate to see a young person get away with cheating because it is unfair to those who do their work honestly. Also, you would like to see students learn their lesson early in life before they make mistakes that can ruin their life. Can we eliminate the possibility of making type 1 and type 2 errors? Unfortunately, no. If we are so afraid of a type 1 error occurring, punishing an innocent person, we lower our alpha value so only students who are literally caught in the act of cheating are punished. We have to be 99.999% sure that the student cheated before we punish him. But that means that more students who actually cheated will get away with it. In other words, when we decrease the probability of a type 1 error occurring, the probability of a type 2 error increases. Think of it as the scales of justice. When one side goes down, the other goes up. Similarly, if we want to be sure that a type 2 error doesn't occur, that students never get away with cheating, we will end up punishing students for whom the evidence that they cheated is marginal. We are, in effect, raising the alpha value. In other words, when we decrease the probability of a type 2 error, we increase the probability that a type 1 error occurs. You really have to decide what is important to you, not punishing an innocent student or not letting students get away with cheating. You can't have both. Now that we have defined type 1 and type 2 errors, what are the probabilities that they occur? Type 1 and type 2 errors are not complementary events. Their probabilities do not add to 1. You can control the probability of a type 1 error as its probability is its significance standard, alpha. For instance, if you do a hypothesis test at a typical 5% level, the probability that a type 1 error will occur is 5%. That means that 5 times out of 100, you will end up accepting the alternative hypothesis when the null hypothesis is really true. Since you control the significance level, you control the probability of a type 1 error. The probability of making a type 2 error is called beta. Its calculation is not covered in the AP curriculum. However, you do need to know the power of the test, which is 1 minus beta. If the probability of a type 2 error is 3%, then the power of the test is 1 minus 3%, or 97%. Realize that since when the probability of a type 1 error gets smaller, the probability of a type 2 error gets larger, and thus the power of the test gets smaller. And when the probability of a type 1 error gets larger, the probability of a type 2 error gets smaller, and thus the power of the test gets larger. Here's another problem, this one a bit more serious. You go camping in the woods. When you get home, while taking a shower, you find a tick on your skin. You are concerned that you have Lyme disease. You go to the doctor and he gives you a test. Although the test for Lyme disease is a very dependable one, it is not 100% reliable. Let's think about this in terms of hypothesis testing. Your conjecture is that you have Lyme disease. Remember that the null hypothesis is the opposite of your conjecture. So HO is that you don't have Lyme disease, and HA is that you do have Lyme disease. One of these statements is true, but unlike Andrew's cheating, no one really knows for sure which one is true. There are tests for Lyme disease, but the reliability is not 100%. So your body knows whether it has Lyme disease, and weeks later it may become clear, but the damage has then been done. You want to treat it in its earlier stage, but how do you know whether you really have it? So you take the test for Lyme disease and the results come out. Remembering this template for type 1 and type 2 errors, amend the table for this particular problem. A type 1 error is concluding that you do have Lyme disease when you don't have it. The test is giving what is called a false positive. A type 2 error is concluding that you don't have Lyme disease when you do have it. The test is giving what is called a false negative. The humorous graphic does a good job of describing these terms. A type 1 error will give you needless worry as well as needless time and expense. Also, you will be getting a treatment that might give side effects when you didn't need it. But a type 2 error means that since you do have Lyme disease, time will go by before it shows itself in a bad rash, swollen joints, and neurological symptoms. Treatment is much more effective in the early stages, but you thought you were safe. Which error is worse, in your opinion? Most people might decide that the type 2 error is worse, but remember, if we try to lower the probability of a type 2 error and increase the power of the test, we increase the probability of a type 1 error and create a lot of false positives, meaning that more people will be treated for a disease they do not have. So now you take a crack at doing one. In the days after the terrorist attacks of 9/11, airport security completely changed. Before 9/11, you only had to show ID when you were checking in, and only to the airline, not the government. Only 2 questions were asked. Did you pack your own bags? Have your bags been outside your control? You could bring sharp objects on the plane such as penknives, box cutters, and sharp scissors. You never had to put your shoes through a metal detector. All you had to do was arrive minutes before the flight, and you wouldn't have to rush to get on. Family and friends could accompany you to the gate and say goodbye. 9/11 changed all of that. The conjecture now is that anyone getting on a plane is a terrorist threat, and security has changed to reflect that. Create the null and alternative hypotheses and a type 1, type 2 error table as shown previously. Explain what a type 1 error and type 2 error are, the ramifications of each, and in your mind, which is worse. As before, the null hypothesis is the opposite of the conjecture. We assume that the passenger is not a terrorist threat, and the alternative is that he is a terrorist threat. Security people screen the person based on the security technology they have. They make a decision that a person is not a terrorist threat or that he is. The type 1 error is that security believes that the passenger is a terrorist threat when he is not. The type 2 error is that security believes that the passenger is not a terrorist threat when he really is. The ramifications of a type 1 error is the type of security we have today. Taking off shoes and belts, no liquids, having all your possessions scanned, and invasive procedures. You have to arrive earlier to the airport, and the security process is stressful. There are concerns that personal rights are violated. But a type 2 error means that a terrorist might get on the plane and another 9/11 could occur. Most everyone agrees that a type 2 error is far worse than a type 1 error. As we have seen before, type 1 and type 2 errors are related to each other. We are so determined that another 9/11 never be able to occur that we try to be as close to 100% sure that a type 2 error not be possible. So that leads to increasing the probability of a type 1 error occurring with security people doing exhaustive searches of 80-year-old women and small children. Finally, please watch this clip from the 1957 black and white movie 12 Angry Men. Navigate to 22 minutes 55 seconds and watch until 28 minutes 25 seconds. This movie is considered a classic and demonstrates what can happen in a jury room after a murder trial. This supposedly open and shut case proves to be anything but. As you watch it, think about the null and alternative hypotheses in a murder trial and how the concept of type 1 and type 2 errors are subtly discussed in the clip, as well as the issue of the alpha significance.